It is an colorless, flammable hydrocarbon with a sharp aromatic odor. To the world, it is cumin. To the engineers, it is the backbone of the hot process.
Cumin is synthesized through the alkylation of benzene with propylene by using the acid catalysts such as phosphoric acid and the ZOS. The chemical equation for the synthesis of cumin is C6H6 react with C3H6 to produce C9H2.
Starting from the left side of the process flow diagram, benzene enters the system as a liquid stream and is first sent to a centrifugal pump. The pump increases the pressure of the liquid to overcome friction losses in the piping system and ensures smooth transport to downstream units. At the same time, propylene enters as a gas stream and passes through a compressor, which increases its pressure so it can be effectively mixed with the benzene stream. Both streams are then sent to heat exchanger 1, where the temperature of the streams is adjusted to reach suitable operating conditions for the reaction. Proper temperature control is important because the alkylation reaction is exothermic. Next, the streams enter the reactor, where benzene reacts with propylene to produce cumin, and also producing diisopropyl benzene as a byproduct. The reactor outlet then flows into a flash drum, which separates the mixture into vapor and liquid phases based on differences in volatility. The lighter components, mainly unreacted gases, leave from the top and are sent to a heat exchanger and separation unit for recycling, while the heavy liquid stream continues to the separation section. The liquid stream is then sent to distillation column 1, where benzene is separated and recovered from the overhead stream so that it can be recycled back into the process. The heavier mixture containing cumin and diisopropyl benzene leaves the bottom of this column. This bottom stream then enters distillation column 2, where cumin is separated as the main product, while diisopropyl benzene is removed as the heavier bottom product.
Next, I will present our non-reactive unit operation analysis focusing on mass balance and energy balance for distillation column 1. The purpose of this column is to separate components in a mixture based on their volatility differences. In this case, the fixed mixture contains benzene, cumin, and diisopropyl benzene. For the mass balance, several assumptions are made. The feed molar flow rate entering the distillation column is 500 kmol per hour. The feed composition consists of 80.03 mol% benzene, 90.96 mol% cumin, and 0.01 mol% DIPB. To simplify the analysis, we assume that 100% of benzene is recovered in the overhead stream, while the heavier components, cumin and DIPB, leave through the bottom stream. This assumption reflects the fact that benzene is more volatile than the other two components. Next, we perform a degree of freedom analysis to determine the number of unknown variables and independent equations. From this, we can calculate the unknown molar flow rates for the alert streams of the distillation column. Consequently, we determined our overhead flow rate to be 400.15 kmol per hour and our bottom flow rate to be 99.85 kmol per hour. After obtaining the molar flow rates, we proceed to determine the mass flow rate and mass fractions for each component. This step converts the molar basis into a mass basis. Moving to the energy balance, we set our reference state for all three components as liquids at 25 degrees Celsius and 1 atm. Using these reference conditions, we determine the specific enthalpy values and calculate the enthalpy change. Since the feed enters at the reference temperature, its initial enthalpy is 0. However, product streams require significant energy. The overhead benzene exists at a vapor at 80 degrees Celsius, requiring us to calculate the sensible heat of liquid, the heat of vaporization, and the sensible heat of the vapor, totaling 38.403 kJ per mole. For the bottom streams exiting at 150 degrees Celsius, we integrated the specific heat capacities to find the enthalpies of 32.851 kJ per mole for cumin and 32.969 kJ per mole for diisopropyl benzene.
Now, we move to the heart of production, which is alkylation reactor. This reactor involves two reactions. First is main reaction, benzene plus propylene producing cumin, and the second sub reaction is cumin plus propylene producing diisopropyl benzene. In this model, we are feeding the reactor with 100 kmol per hour of propylene and 500 kmol per hour of benzene. For this reactive reaction, we have four parts of calculation: input, consumed, generated, and output.
To find the flow rate of input, we just get the summation of 100 kmol per hour of propylene and 500 kmol per hour of benzene. To find the flow rate of consumption of propylene, we just assume that 99% of propylene is used. For benzene, we just compare 1 mole of main reaction propylene equal to 1 mole of benzene. For cumin inside reaction, we just do the comparison. The total flow rate of consumption is 199.80. Next, to find the flow rate of generation of cumin in main reaction, we just do comparison. We do the same thing for diisopropylbenzene also. Therefore, the total flow rate is 99.90 kmol per hour. To find the flow rate of output, we just use this formula. Output equal to input plus generated minus consumed. And we get the flow rate of propylene, benzene, cumin, diisopropylbenzene. Hence, the total flow rate of output is 500.10 kmol per hour. Next, we should find the mole fraction. First, in feed. Second, in product. Lastly, finding mass fraction. In feed, we should find the mass flow rate by multiplying flow rate and its molecular weight. Mass flow rate of propylene, we got 4,208 kg per hour. And for the mass flow rate of benzene, we got 39,055 kg per hour. Then we should find the mass flow rate of feed, 43,263 kg per hour. As usual, to find the mass fraction, we should divide the mass flow rate with its total mass flow rate. As for in product, we do the same thing as we do in feed, and we got this value of mass fraction of propylene, benzene, cumin, and diisopropylbenzene.
Next, we are trying to perform an energy balance for this reactivity. Firstly, this is our reference point. For benzene, we have liquid 80 degrees Celsius and 20 atm. For propylene, we have vapor 80 degrees Celsius and 20 atm. And lastly, for cumin, we have liquid 120 degrees Celsius and 20 atm. And this is our table with level.
Since H1 and H2 does not have change in temperature, its value is 0 kJ per mole. To find the change in enthalpy of H3, we just use this formula with the information in B2 table, and we produce 3.05 kJ per mole. Next, to find the change in enthalpy of H4, we just use this formula and produce 5.55 kJ per mole. To find the extent of reaction, we just need to minus 400 with 500, and with its absolute value, we divide it by 1, and it's equal to 100 kmol per hour. To find the standard heat of reaction, we just need to find the standard heat of formation of each molecule in the table and use this formula. And we get negative 92.81 kJ per mole. And finally, we can calculate the heat of reaction by inserting to this formula. And we get negative 7,105 kJ per hour.
However, the real challenge is the movement. At our sensitivity, cumin is treated as an impressible of fluid. We monitor the Reynolds number calculated by using this formula. The liquid flow through the pipeline can be categorized into three regions. If Reynolds number is less than 2,000, then it is classified as a laminar flow. If the Reynolds number is between 2,000 and 4,000, then it is classified as transition flow. Then after that, the last one, if the Reynolds number is more than 4,000, then it is called as turbulent flow. Resistance from the fluid friction and pipe wall roughness cause the pressure drop, which is a major loss. In the laminar flow, the friction factor formula is as below. If E is turbulent flow, the formula is. If E is the transition flow, the formula will be this. Other than that, we also use the Bernoulli equation and total friction loss formula.
Moving on to the piping layout, this process uses stainless steel schedule 40 pipelines with different diameters depending on the flow conditions. Smaller 2-inch pipes are used for moderate rate flows, while larger 3-inch pipes are used for higher flow rates to reduce pressure drops. Each pipeline includes fittings such as gate valves, check valves, and 90-degree elbows, which influence pressure losses in the system. Using fluid mechanics principles such as the Reynolds number, friction factor, and Bernoulli's equation, the pressure drops across selected pipelines were calculated to ensure that the pumps and compressors can provide sufficient energy for fluid transport.
This is the step-by-step and formula to find the change in pressure for pipe 1, 6, 8, 9, and 10. By assuming each pipe's properties accordingly, this is the simplification of change in pressure of each pipe.
Regarding the strategy to deliver the main product, we have decided to use stainless steel 2-inch SCH40 as pipe material. The pipe will transport cumin to a stainless steel cylindrical tank with 4 meter internal diameter, 12 meter height, in which it will have a maximum capacity of 150.5 meter cube. With this capacity, we maintain a 20% safety buffer, keeping the product stable between 15 and 30 degrees Celsius. In order to get the estimate production rate and pressure difference, the calculations are as below.
In conclusion, this project demonstrated the conceptual design of a cumene production process through the combination of benzene with propylene. By applying the principles of chemical engineering, we developed a process flow diagram consisting of key units such as pumps, compressors, heat exchangers, a reactor, flash drum, and more. Mass and energy balance calculations were performed to verify the feasibility of the process, while fluid mechanics analysis was used to evaluate pressure drops and pipe performance. Overall, this project highlights how fundamental engineering concepts work together in the design and operation of an industrial chemical plant.